Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon.
It is after morning, that's true.
It is. Good afternoon. Good whatever. Good afternoon. 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 Good afternoon.
Afternoon, sir. I think it's afternoon.
Good afternoon.
Oh, afternoon again.
Good afternoon. Good afternoon. Good afternoon.
Barely.
Good. Huh?
It's only barely morning now.
It's afternoon.
Is it? It's not afternoon, sir. There's still a good 4 minutes left in the morning. I will treasure it.
Okay, good. Good afternoon. I keep the options open, you know. Good afternoon. Good afternoon.
This afternoon, good afternoon.
Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon.
Well, not salted, but I was
Good afternoon. Good afternoon.
I was on coffee.
Good afternoon. 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 It's in between. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon.
Yeah.
It's afternoon. It's fluent. Fluid. Good afternoon. It's either. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. It's fluid. Good afternoon. We do a compromise. Afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Good afternoon. Right, let's make a start. A most wonderful good afternoon, ladies and jelly beans. It's wonderful to see so many people here despite Wednesday. I know there have been a few victims, but hey ho, they probably watch it at home or from bed or wherever. So wherever you are, hi folks. Please don't forget to register your attendance. As per usual, it's on Moodle. And just a brief reminder that quiz 2 in BI 308 will close this Sunday at 5 p.m. And do yourself a favor, if you haven't submitted, do the quiz in time because you don't want to get stressed about things, right? So please do submit before Sunday 5 p.m. And for those who are checking the quiz website, you probably have noticed there is another quiz, quiz 3, but I will email you the link in tomorrow's email. Quiz 3 is a very simple quiz. It's only 10 questions for you guys, so easy stuff. And it counts double. And you have until the 15th of March. But of course, there's a little twist to it, which you will surely discover. It's no longer a click, 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 click. You have to do a little bit of work for that. And don't be surprised, you won't see a mark or a score for that, because you have to answer all questions. It's a sort of a pass or fail test, but it counts 6% in the aggregate for the quizzes. So I hope you enjoy it. Actually, I asked my daughter whether I should be really mean with it, but she discouraged me. And she said, look, they are poor students. Don't be too horrible. So I've been nice to you guys. Have a look at it. I had some fun with it. Okay, so last week, we fuffed around with these IQs and normal distribution, and we had the question, what are we going to do if the conditions don't really apply for a normal distribution? And right at the end, I said we have to then switch to a different kind of distribution. We have to switch to what is called a T-distribution. And I want to give you a typical example for one of the applications of the T-distribution. Oh, I can't read that, what the comments say. I probably have a look. Oh, watching from the final year project labs. We miss you. Oh, Rita, that's really nice. They are final year students. They obviously don't have anything better to do. Hey, go back to your experiments, Rita. Okay. We have a typical scenario where we need to apply a t-test. I better not bait that. So let's say we test 3 people for a metabolite in the blood, and we find concentrations 5.5 millimolar, 6.9 millimolar, and 4.4 millimolar. So that's a group of people who we test. And we know that a healthy person has a concentration of 12.7 millimolar of this metabolite in the blood. Are these 3 individuals where we took blood samples, are they healthy or not? Yes or yes? Emily says no. Emily says no. Good. Okay. Why? They're lower. But it could be, wouldn't it be possible that there might be sort of a chance that they still might be okay? Maybe. I love that, how I can sort of plant the seed of doubt in people. It's really brilliant. Actually, we already have a tool at our disposal where we can do a sort of a check. Is it possible that these are healthy or not? The second or in the third lecture in this module, what we can do is we can calculate a confidence interval, a 95% confidence interval. And you have done that quite extensively. Some people even tried to do it in the in-class test, where it was exactly the wrong thing to do because you were supposed to do a Poisson distribution and not basically 95% T distribution, which you're doing. But we can actually do that. We can basically say, right, let's calculate the average of that. And we know how to do that. We add them all up, divide by 3. And if my calculations were correct, it would be, the average would be 5.6. Okay? We can also calculate a sample standard deviation. And again, you know how to do a sample standard deviation. And in this case, it would be 1.25. And we know that we can calculate the margin of error for that. So margin of error equals a critical t-value times s over square root the sample size. So all we need to do is find the critical t-value. And again, you've heard that quite frequently for a sample size of 3. So if n equals 3, we have the degrees of freedom, in this case, is n minus 1, so that would be 2. And for 95%, confidence interval, our T critical would be 4.3. All we need to do is we need to plug in our numbers. So margin of error would be 4.3 times 1.25 over square root 3. And if we did that, we would get, say, 3.1. That's our margin of error. And we can calculate the upper and the lower bound. For our data, we know that the upper bound, that is our average plus the margin of error, and the lower bound is the average minus the margin of error. So we would get 3.1 plus 5.6. That gives us 8.7. And for the lower one, it gives us 2.5. Is that right? Yeah, I think so. So that's really our 95% confidence interval that we can calculate from our little sample here. So what does that look like? So here we have our average, sample mean, 5.6. Here is the upper bound, 8.7, and here's the lower bound, 2.5. And we say 95% of the time, 95% if we did this experiment very, very often, we would find things here. So far, so good. Now, where's our reference value? Is the reference value within the 95% or outside? It's outside. It's somewhere here, probably. 12.7. So the reference value is way out, which very nicely indicates that Emily was totally right in her assumption that, well, these three characters that just schlepped in are not healthy. Yeah? Now, of course, this is just sort of looking at the data. With the confidence interval, we can say, right, the reference value is outside the confidence interval. We can also ask the question, if we don't want to go down the route of the confidence interval, what is the probability that we actually get something special here? We can ask, are these three people special with respect to the reference value? And with the confidence interval, we already know they are special. So are they special? Like we did with, Kieran and Alex and Ellie. Are they special with their IQ last week? But we have a problem. We have a conceptual problem here. Because last week, we had it exactly the other way around. Last week, with the IQ, we had a sample mean and we had a population mean and a population standard deviation. And we compared, for example, Alex's IQ to this value, to this range, and asked whether he is special. Now we have exactly the opposite, if you think about it. We have a reference value, but we don't have a population standard deviation. But actually, if you think about it, it's not terribly difficult to make this next step. Because we could turn that around and we could say, right, why don't we just simply ask the question whether the reference value is special compared to what we get from these three individuals? It's a little bit like saying, I am 3 meters away from Ben. So the big question is, how far is Ben away from me? Of course, it's the same thing. It's 3 meters, yeah? So what we can actually do is, if we don't have a population standard deviation, we just simply treat our sample like the population and compare the reference value. And we say, right, let's see whether the reference value is special to that. And of course, we can't use a normal distribution because A, our sample size is really small, we've got only 3, and we don't know the population standard deviation. But we know the sample standard deviation. Let's just do an estimate with that, and let's work through it. We know that we can't use a normal distribution, but we can use a t-distribution with that. And as we've done with the normal distribution, we can very easily calculate a t-score, or in this case, it is called a Ttest score, or Ttest. And it's basically exactly the same as we've done with the normal distribution. But we have to bear in mind, it is a sample. We have a sampling distribution in this case. So what we can do is we can calculate how far away is our reference value of 12.7. How far away is that from our 5.6 from the, our sample mean? And we just simply divide by s over square root n. And if we do that, what do you get for that? What do you get? Can somebody do me a favor, please, and try to calculate that? You lot out there? Have the trails run? Anyone? Do I have to do that in my head?
9.83.
Let's say 9.8. Yeah. Thank you very much. So that's our test score. It actually means that this 12.7 value is 9.8 sort of these standard deviations away, sample standard deviations, away from the average. How do we have to envisage that? Here's our t-distribution. Note, it has really fat tails here. They're quite big. They look different to the normal distribution. Here's our center, 5.6. And here are our critical values. These are the critical values that we had previously for our confidence interval, 4.3 and negative 4.3. And we are now asking, what is the probability that we actually get this value of 9.8? Is the value of 9.8, is it special? If we compare that to this area here is 95% of our data. Is 9.8 special? What is the probability that we get a value of 9.8? Where would it be? It probably would be somewhere here. So probably should put this here as 0. So here would be our 9.8, the t-value, the t-test score. What is the probability that we get this test score? Is it larger than 5%? No, definitely not, because we know that this area here and this area here together are 5%. We know it's probably even much smaller than 2.5%, because this part here, that would be 2.5%, and this area here would be 2.5%. So it's much smaller than 2.5%. So if we ask what is the probability to get this t score, we know it's much smaller than 2.5%. Luckily, we don't have to look it up in t-tables. You probably have done that at school with t-tables. Yeah? No? Some did. What we just simply can do is we can go into Excel, and Excel has a nice function for that. Let me go back to my scribbles. The function in Excel is equals t.dist dot 2t. It's a very, very useful function. It gives us the value for a t distribution, and it checks whether it is special. If our function has two tails here, so if it has this one here and this one here. Sometimes we are interested only in one side of it, but most of the time when we say we want to know whether it is special, it could be that it is larger than 4.3 or much smaller than negative 4.3. So it could go either way. So therefore we use usually a t-dist 2t. And just quickly need to here. And the argument is our t-test score and the number of the degrees of freedom that we have. So here we have, bless you, equals t-dist 2t 9.8, and we have 2 degrees of freedom. And if we try to do that in Excel, I've just put that in. We get a p-value of 0.01, or if we want to express that in percent, is 1%, roughly. So the probability that we get this t-test score of 9.8 with our metabolites here, and they are not special, would be 1%. There's a very small chance that we get it, that we get this result, if they are not special. Does that make sense? A very small probability that we still get that if they were not special. So we can use this this trick to very nicely calculate if we've got a set of data and want to compare that to a reference value. We can calculate the t-score, as I said, t-score or t-test. We just take our reference value minus our sample average divided by the standard deviation over square root n. We get a value for that. What's that? My eyesight is so bad. What was this comment? I hope nobody says no. Hi. Okay. Good. Hi. Good. Hi. We get a t-value, and we just simply then check what is the probability that we actually get this t-score if we assume that there is nothing special about the sample that we have. Maybe you can already spot a little flaw in the thinking here. First of all, what happens if the reference value is smaller than our average? Then obviously we would get a negative t-value, right? You will probably discover that Excel can't deal with that very well. But actually, it doesn't matter, because all we are saying is, well, if the reference value is negative, then it's somewhere over here in our distribution. And all we need to do is we just simply say, is it special or not? So what we can easily do is we just simply say, we take the absolute of that. So if it is negative, we just simply ignore the negative sign. If it's positive anyway. Yeah. So it doesn't make any difference. And I indicate that with these two vertical lines. So that's not a problem. What would happen if we increase our sample size? Instead of 3, let's do the whole thing with a sample size of 10,000. So we have, what was it, 12.7 minus 5.6 divided by 1.25 over square root 10,000. So we get 9.8. No, sorry, what is 12.7 minus 5.6 is 8.1. Is that right? 7.1. Thank you. Don't have a good day. So we've got 7.1 divided by 1.25. Square root of 10,000 is?
568. No, this one.
Oh, for the whole thing?
Yeah.
Okay. So square root of 10,000? It's 100. Yeah? 1.25 divided by 100 is 0.0125. And what did you get, Camille?
568.
T equals 568. The bigger our sample size, the bigger the massively bigger we'll get our t-value. Now, of course, we could try and find out what is the probability to find a t-value like that from our sample distribution. It would be basically 0. In other words, even if we have a value, even if we have a t-value that lies, say, here, if we increase our sample size, the t-value would move outside the range just by increasing the sample size. In other words, if you want to prove that something has an effect, that something is special, all you need to do is increase the sample size. So you can, for example, say, you measure the scores of 20 people in their A-levels. You find that they are nicely within a normal distribution or even within a t-distribution. There's nothing special about these 20 people from a given school. But if you take all the pupils from the same school, your sample size goes up, and all of a sudden you will find, oh, wow, cool, hey, there is an effect. There is an effect because the p-value really goes down. It becomes really unlikely that these are just bog standard students. How can we overcome that? Luckily, there's a very, very simple trick, which usually you don't get told. Apart from me, of course. This thing is called the effect size. And there are a number of different ways how you can calculate an effect size. But the most common one is called Cohens D. And that's sort of an empirical thing. And the way you calculate Cohens D is very, very simple. Cohens D is reference value minus your average, and you take the absolute, so it doesn't matter which one is bigger. If it's negative, you ignore the minus sign. If it's positive, you just leave it. And you divide it by S, simply by the standard deviation in this case. And if we did that, we would get a Cohens D value of, let me just do that, 12.7 minus 5.6 divided by 1.25. Can you do that? You are quick. .7, right? Thank you. So Cohens D value is 5.7. Huh? So what? Who cares? Actually, by convention, a D value which is larger than 0.8, and that's just a sort of a convention. Cohens D over 0.8 is considered as massive. It means there is a massive difference between the reference value and our sample mean. If it is below 0.8 but larger than 0.5, so in between, it's considered as quite big. If it's smaller than 0.5, then it is considered as, well, there might be an effect. If it's smaller than 0.2, then people would usually say, well, don't bother. Let me give you an example for that. What does that mean? Let's go away from the metabolites to something that is more, palatable. Bags of crisps. They usually come in some really odd weights, 56 grams or something like that. Does anyone have a bag of crisps here? No crisps? Oh. So, usually they come in, let's say, 56 grams or 50 grams. And that is what it says on the bag. 50 grams should be in there. Now you are interested, is that true? Or is the producer of the crisps, is they lying? Are the mean people who just put in 45 grams of crisp and say it's 50 grams of crisps is in the bag? So what you can do is you can weigh some of the crisps. You take, say, 9 bags of crisps, get your value, and you find that actually the mean is 48 grams with a standard deviation of, say, 2 grams. And what you can do now is you can say, what is the probability with these one sample t-test that I just showed you? What is the probability that I get 48 grams if everything is kosher, if everything is good, with a 50-gram bag? So I can calculate that. And you probably find out that there's a little bit not right. They are cheating. Because actually, there should be a little bit more crisps in there. Or you find, it can happen. With a sample size of 9, it is possible that the average is 48 grams of crisps. It's within the confidence interval. Now, if you increase the sample size from 9 to 10,000, you will find, oh, wow, there is an effect. The guy is cheating. Walkers are, liars. Just simply because your t-value goes bigger and bigger. But then you do a Cohens D, and you find actually really not a big deal difference. You might find with this calculation that it should be 50 grams, but actually what you find, it is 59.9 grams. So it's 0.1 gram difference to what it should be. Does that really matter? This 0.1 gram of crisps? Last year I had somebody in the lecture who was absolutely adamant, yes, it does matter. They are cheating, it's the principle, and it's this 0.1 gram. I want this 0.1 gram. And I said, okay, take Walkers to court. It doesn't matter. the effect size, the difference is so small actually that nobody gives a damn about it. But there is an effect. So you would use Cohens D. It only makes sense to use this effect size if you find there is actually your sample is special. Your sample is outside what you would expect, let's say 95%. So if the p-value is small, that indicates the sample is special. Let me write that down. If p-value is small, this indicates the sample is what I call special. It is outside the expected range. It's outside the expected range. What is this comment? That's a very good question. I come to that question in a minute. Outside the expected range, the p-value, and if it is outside the expected range, let's say 95% range, then you can say, is the effect big? If it is within expectations, it doesn't make sense to say, is there a big effect? No, there isn't a big effect. There's no effect because it is what you would expect. Right? Now, the question is, would you ever have to do something like that, finding a p-value in an exam? The answer is, only if I have a really, really bad day, which I usually don't have. Of course not. I mean, how could you calculate a p-value? The p-value is actually a rather complicated integration of the t-distribution or the normal distribution. I can't do it by hand. I can't even do it on a computer, the integration of that function. Actually, for the normal distribution, I think it is a non-integratable function. So even with the best will in the world, you couldn't do it. So don't worry. I'm not going to ask you to calculate a p-value in an exam. But I will ask you to calculate p-values with Excel in quiz 4. Yeah? But there are video tutorials that show you how you can easily deal with that, how you can calculate that. Are you happy with that? So, what you have seen is a one-sample t-test where we compare one sample with a given reference value. And I showed you the really long-winded version, how you can calculate a t-score and then convert this t-score into a p-value. And I told you that if we have a very small p-value, if we find that our sample is actually special, then we can do a Cohens D effect size calculation and ask, is there a big effect? So, give you an example. A couple of years ago, I teamed up with a clinical hypnotherapist to help students with exam anxiety. And we did 3 sessions with the students, and they had to measure their anxiety, test anxiety, exam anxiety, before we started the intervention. And then the hypnotherapist did their thing, and we measured the exam anxiety after the intervention. Lo and behold, it went down. This is what we hoped for. We did a statistical analysis, and we found actually, yes, it is, the p-value is very small. That means there is something going on. We wanted to know, does it have an effect, or is that just simply through the statistics that we see? We did a Cohens D, and we found a value of 2.5, which means, by what I just told you, it had a massive effect on the students. Just 3 sessions of clinical hypnotherapy, group sessions, where we helped people just to overcome their anxiety. Would you be interested in something like that again this year? Yeah? Do we have people with anxiety? Nah. I might think about it, if we can do that. So that is Cohens D. What happens, however, what happens if we have not just one sample, if we have 2 samples to compare with? Let's say we have metabolites of one group, and we want to compare it to the metabolites of another group. Is there a difference between these 2 samples? Is there, for example, a difference between the lung function of people who smoke compared to people who don't smoke? That would be a 2-sample Ttest. And how we do that, I show you next week. Go in peace. Don't forget, attendance monitoring, quiz 2 and quiz 3 is open as well.